Happy Shark Week. Today we have a Codeforces round to celebrate. So this is Educational Codeforces round 111. Good luck if you're participating. And yeah. Either AI is 1 or at least one of the numbers exists in the array. Okay. Minimum possible size of a beautiful array with sum of elements equal to S. It's just like the perfect square that's greater than or equal to, yeah. Okay, what's the size? I don't want to use math.square root. Um, you know what? I'll just use it. This should be good. I'm afraid there'll be like decimal precision errors. Why is this C++? Okay, hopefully no one hacks me. Choose some consecutive substring of equal characters. Oh, of equal, okay. The maximum number of points you can score. Okay, so this A times L, the sum of the A's will always be the length. So you want to A times the total length plus B times the number of deletions. So you want to maximize the number of deletions. So you want to maximize the number of deletions. Oh, but B can be negative, okay. So if B is negative, minimize, otherwise maximize. Okay. So what are the inputs? N, A, B. Otherwise, okay, so we have to count how many runs there are. You know what, let's take a char array. If input j equals prev, if input j is not prev, then runs plus plus prev equals input j. Numbers are small enough, okay. 6, 15, negative 6. Negative 2. Oh. Okay, so if there are 3 runs, then it takes 2. If there are 4 runs, then it takes 3. 5 runs, then it takes 3. N plus 2 over 2? Runs plus 2 over 2. This is very sketch, but I think that's right. If there's 1 run, it's 1. If there are 2 runs, it's 2. If there are 3 runs, it's 2. Yeah. Should be good. Okay, nice. Why is the memory so much? Manhattan subarrays. Three points form a bad triple if wait, so what does this mean? This means Q is in the subrectangle formed by P and R. Q is in the subrectangle formed by P and R. Let's say that this array is good. It's impossible to choose. Okay, wait, so what does that mean? That means none of these things are in subrectangles. Wait, so something is in a subrectangle if the x's are increasing and the y's are increasing. Wait, so what's the question? The number of good subarrays of A. Okay. Probably like once you find something is bad, then like all subarrays of that should be good. Okay, so the y's are always increasing. So you just need to make sure that 3x's aren't increasing in a row. Okay, so these should all be good. So this is 10. This is this is 15, but oh, so either they're increasing or they're decreasing. Wait, no. Oh. Okay, so can you find 3 increasing? Wait, so I feel like there's a limit to the size of a good subarray. Like, can good subarrays even be of size 6? See, okay. Let's try and build one. 1, 9. So this one can't be bigger than 9. This one's 6. And then the next one can't be less than this one. Can't be less than 6, can't be bigger than 9. Wait, also can't be bigger than 6. Wait, so no subarrays of length greater than 3 are good. I think. Wait, let's say it's 190. 190, it can't be less than 0. It can't be bigger than 9. Wait, 190. Okay, you know what? It doesn't even matter. We can just try everything, say, like, less than 6 or something. I know there's, like, a limit. Okay, so try all subarrays that are length less than or equal to 6 and just brute force check if they're good. So how many subarrays is that? 6 times 20 times 2 times 10 to the 5th. Should be good. Wait, how many people have solved this? Wait, I think I have the idea though. Okay. Okay, so first all the ones of size 1 and 2 are good. So wait, it's an int. So that's 2 times n minus 1. And then for we can literally brute force check if they're like three consecutive decreasing stuff. Wait, but I'm fairly sure that we can check like less than or equal to 4. You know what, let's just check 5. I'm just worried all these loops will like take up some time. So you have I, J, K. Okay, so if okay, so if there's a decreasing sequence, then break, and if there's an increasing sequence, then break. And then if found is false, then you haven't found one. So s plus plus. Seven, 9, 3. What? Oh, j is I plus 1. And k is j plus 1. 10, 12, 3. Yeah, whatever. I think this works. Yeah, 170. I was afraid to add the check for length 6 because maybe like too much time. Wait, no one solved D. Wait, how are we doing? Oh wow, you're doing pretty good. Okay. No one solved D. Let's just take a look. Wait, I want to try D first. Alright, let's read both. So we want to maximize this value. Wait, what just happened? Let fi be the maximum length substring of string s, which consists entirely of the Latin letter. What? Oh, like, I guess all the same letter? Okay. The value of a string is the minimum value among fi. The minimum value among fi. So you want to maximize that? Wait, here, oh wait, what is it? Fi is the maximum length of a substring. Okay. So here it's 4 and 4. Here it's 4 and 6. So we want to maximize the minimum of the maximum. God, holy crap. Maximize the minimums of the maximum. Two. Minimum of those is 2. Wait, this seems pretty hard. Let's read D. Oh no, 3 people have solved it. Wait, so why is this 2? Oh, because they're 4 letters. So A, B, B, C, C, D, D. And you can't make it 3. Can you binary search? So binary search 0 to, okay. And then how do you check if that's possible? Okay, so for A's you need everything to be more than some, or you need one contiguous string. Okay, this array is good if this, and then f of A is the number of pairs such that, okay, let's say that an array is excellent if A is good Is this math or DP? Or both? Wait, what? Oh. F of A is the maximum possible among all good arrays of size n. These definitions are confusing. Wait, so what is this, like AI minus I equals J minus AJ? So like if you subtract I from everything, it's the number of opposite sign pairs. Yeah, I know how to calculate this, but let's go to Zyboard. Okay, we're given N, L, and R. F of A is the maximum possible among all good arrays of size n. So what's the maximum you can get? Well, the maximum you can get is if that array has like 2 equal, or no, that array has 3 equal. So it's 2, 0, 1. Wait, what? No, 2, 0, 0. 2, 0, 0. Wait, how's that excellent? Oh, okay. Oh my god. Okay. 1, 1, -1, -1. Yeah, yeah. I thought it was 0 indexed. Okay, -1, 1, 1. 1, 1, -1. Okay, yeah, this problem I think is easier. So what is this? This is 2, -2, -2. Okay. So the maximum if like half of them are positive some number and the other half are negative. So it's like x, 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 negative x, negative x, negative x, negative x. And then we need this to be in L to R. So if we convert back, x plus 1, x plus 2, x plus 3, 4 minus x, 5 minus x, 6 minus x, 7 minus x. And these all have to be within some range. Is this anything special? Wait, no, it's not worth. Okay, so let's try this case. So it's 4, so let's say it's like, and it can't be all zeros because the first one, wait. Wait, no, it can. Wait, so what happens if it's just 1, 2, 3? No, 3, 2, 1. Wait, no. Yeah, 1, 2, 3. Oh, okay. That's what this condition's for. So it's not 0. Okay. So let's say, oh wait, how many numbers are there? 4. Okay, so it's 1, 1, -1, -1. And then you just add 1, 2, 3, 4 in some order. So here you can do anything. No, you can't do anything. They have to be within -3 and 5. Wait, what? Why can't you do anything? Oh, so you do add in this order. You can just rearrange these. Okay, so that's 6. And then 2, 2, negative 2, negative 2. Here, you can't add the 4s to the 2s. Wait, but there will be so many of these conditions. Yeah, 2 times 10 to the 5th. So you can't add the 4s to the 2s. So negative 2 is here. And then the rest you can do anything with. And then what about 3? 3, negative 3, negative 3? You can't add the 4s to the 3, so this is negative 3. And then you can't do the 3 to the 3, so that's negative 3. And then the rest are set. So that's 1. So you have to worry about what's too big, what's too small. Wait, this should be doable. Yeah, so you just loop through, oh wait. So you just loop through this value, x, but what do you loop from? See, this R and L can be really big. Okay, these are hard problems. Okay, so you have restrictions on what's too big and what's too small. Is there a way we can transition in like really quick? So these numbers are staying constant, and then every time you just add 1 here and add 1 here, and then you choose the rest. So it's like n choose r, and then n minus 1 choose r minus 1. Wait, what? N minus 1 choose r minus 1? No, n minus 2 choose r minus 1. And then n minus 4 choose r minus 2. Yeah, so this was 4 choose 2. And then this was what? 3 choose 2. And then we keep, okay. No, I think this is doable. Okay, so in this case, there were no restrictions here. So in this case, it was 4 choose 2, 3 choose 2, 2 choose 2. But in some cases, there may be some restrictions here. So let's say we're like at x, negative x. So the boundary is 1 minus x and 4 plus x. So everything that's greater than or equal to so like k plus x, if k plus x is greater than r, then these have to be negative x. So if k is greater than r minus x, so you find where r minus x is, and then all these have to, and then you find where so if 1k minus x is less than r, so k is less than r plus x. Wait, no, L plus x. So you find L plus x and you find r minus x. And then you choose the rest. This is really messy. I should have moved over. So you find where L plus x is. Find where L plus x is. You find where r minus x is. And then you can choose anything here. Okay, so that's it. And then what do we loop x to? So L plus x. So these have to be within the L to R range. That is a huge range. Oh no, this has to be within the L to R range. And this, maybe that doesn't give a huge range. So 1 minus x has to be greater than or equal to L. No, wait. 1 plus x has to be less than or equal to r. Wait, maybe, wait, so you find L plus x, you find R minus x. So if they're like 2 apart, then you're screwed. So L plus x has to be less than R minus x plus 1. L plus x has to be less than or equal to R minus x plus 1. 2x less than or equal to R minus L plus 1. X less than or equal to R minus L plus 1 over 2. Now, is there a lower bound? No. Oh, so you go until... I feel like this will be really messy. But I think we can solve this. We should be able to solve this. Okay, so x less than or equal to R minus L plus 1 over 2. So we have to check all x's. Wait, what? Oh, okay. And then like sort of, if these are all plus and these are all minus, that's like sort of the best we can do. So the boundaries are 3 plus x and 4 minus x. Three plus x and 4 minus x. What? I'm confusing myself here. So okay, 3 plus x less than or equal to r. 4 minus x greater than or equal to L. X less than or equal to 4 minus L and greater than or equal to... No, we already have an upward bound. Wait, so what's the lower bound? Oh, what? Oh my god. Lower bound is 0. I'm stupid. No, lower bound is 1. Okay. So you loop from r minus L plus 1. Wait, but you can't loop to 0. Okay, you loop from r minus L plus 1. So if, okay, so you loop from r minus L plus 1 over 2. Wait, do you just loop until what? Let's just start coding. Okay. Let's make L and R longs just because. Okay, so for int x equals 1, x is less than or equal to, what were we doing? R minus L plus 1 over 2. That takes the floor, so we might as well just go one higher. Okay, so if L minus, what was the condition? If L plus x less than, if L plus x is greater than R minus x plus 1. So then there are no, so we continue. So otherwise, so if n is even, then we know there are n over 2 x's, n over 2 y's. Otherwise, wait, no, n over 2 plus x's, n over 2 minus x's. Otherwise, either this or that. Okay, so how many are taken? So we find L plus x. So how many are below or equal to? Wait, what? K is less than L plus X? Wait, I'm confused. K plus K is greater than R minus X? Oh. Oh, okay. So L plus X minus 1. Minimum of that and 0. No. Minimum of that and n. And n over 2. Wait, no, and n. Okay. R minus X, num above equals max of R minus X. What is it? N minus R minus X. So n minus R plus X. And then n. Sorry, min. So here we do num pos minus equals. Wait, why are these? These should be num pos minus equals int of num below. Num neg minus equals int of num above. We need the choosing thing. Oh, I have to take a break right now. Alright, my bad. I had a call to attend, but that was like 10 minutes, so let's get back to work. So what were we doing? Choose. We had to implement like choose. How much time is left in the contest? 50 minutes. We can get this. Okay, so choose and choose K. Yeah, so we only need until 2 times 10 to the 5th. Okay, and then we need the inverse function. So then we just need n choose K. I don't even know if I have that method. Oh, no, I do. It's right here. Wait, whoops. I I put this in the wrong class. Okay, and I have to make factorial static. Okay, there we go. So what do we add to this? We add and choose k of, oh no, binom of num wait, is this right? Yeah, numpos plus num neg numpos. Okay, so this will take too long, but I just want to see if it's right first. I think this should work for the first two cases. No, it should work for all of them. Four 27. 27. Why is it 27? I guess let's debug this. 4 -3 5. So x is 1 here. So L plus x is -2. Oh my god, num below. Okay, this is right. 1 4. Okay. So now how do we get this faster? Okay, so once it's okay, we can get this. So as x gets smaller and smaller, x gets smaller and smaller. So if one of them becomes 0, we're doing redundant work. No, we're not doing redundant work. We're just doing it inefficiently. So once num pos gets to 0, wait, so if it's 1, then one is not a problem. So 1 minus 1? Minus x. Once 1 minus x hits L, then we've got a problem. No. If x is greater than L plus, wait. So once L plus x hits 1, once L plus x hits 1, then that starts decreasing. And once R minus x hits 4, then that starts decreasing. So from R minus x equals 4, L plus x equals 1. So x equals 1 minus L, or x equals R minus 4. x equals r minus 4, then you go like n over 2. Just go n, just in case. And then if x equals 1 minus r, then you go n. So wait, this is r minus n. So x is 1 minus L. Okay, and then x is r minus n to r. So these ones you actually want to count. And then the rest of them, these ones you actually want to count. And then the rest of them. So maybe we have, instead of this for loop, so int x equals 1 minus L, x is less than or equal to 1 minus L plus n x plus plus. So this takes care of that. And then what should this be from? Why is this underlined? Okay, so this takes care of that. And then we want to go from this plus 1 so messy. Okay, so, and then for the rest of them, okay, so for the ones in the middle, we just count 1, and for everything below, we just add the total. So you add 1 for these. There's no way I'm debugging this. And then for everything below, you just add so here would be n choose n over 2. Wait, it's always n choose n over 2. That was really messy. There's probably a better way to code that. It's not even right. Okay, I'm gonna undo all that just because I don't want to. Okay, this is what I had originally. Let me just make sure this was the right code. Okay. So let me just save this and then okay, so I saved that. Let me actually try and debug the old one. Never mind, I can't even restore it. Okay, let's just recode this, but cleaner. So you go from L minus X equals 1. So X is L minus 1. No, L plus X is 1. So X is 1 minus L. And then N plus N minus X. No. R minus x equals n. So x is r minus n. Yeah. Wait, I don't get it. This is exactly what I coded. But let's just try it again. So 1 minus L to 1 minus L plus N. And R minus N to R. R minus N to R, yeah. Oh, wait. Once one of them is 0, it's always just 1. Oh my god. Oh my god, okay, that's why I have this. Once one of them is 0. Yeah, once one of them gets to 0, it's always 1. Okay. So for int L equals minimum of 1 minus L, comma R. Wait, what was it? 1 minus L, comma R minus N. Wait. I think from then on it's actually 0. So the answer starts out being n over 2 times, wait, why n over 2 times? No, binom of n over 2 times this minus 1. Okay. Should be it, I think. Hopefully. Four, 10, and then other stuff. Come on, we need to get this. There are probably like 100 people who got this. 200. Why am I oh my god, why am I multiplying by n over 2? Okay, what? Why is this one wrong? Why is this wrong? Negative 42, 146. I don't get n after that. Then it's good, then we're good. I don't know why it's wrong. Oh, that's why. So if L plus X is greater than n over 2, n over 2 plus 1. So then here it would be n over 2 plus 1. Okay, we continue with this, but I don't even need this, right? So maybe the ones how could this be wrong? Minimum of one. Wait, what is this? This is how many. What is this? Yeah, this is how many like before. So if X is before any of this stuff. Okay. 14 minutes. What am I doing? No, I can definitely get this. I'm just being stupid right now. Okay, 1 minus L, R minus N. R minus N. Okay, so that's 43, 42. So for anything x equals 1 to 42, we're good. Anything will work. Oh. Oh my god, if n mod 2 equals 1, then ans times equals 2. Oh my god, right. This should be right. There we go. That's right, right? 698570404. That was really stupid. Yeah, that took way longer than it should have. Well, there's no way I'm getting E in 12 minutes, but we might as well try it for a little. Wait, how are we doing? I guess still not bad. I'm not a trusted participant yet. So if I do... Wait. Yeah, I don't know what place I am in div 2, but... Oh yeah, this problem. Yeah, I need to think about this for a little longer, but I guess we can do solutions for A to D now. Okay. So starting off, problem A. Okay, what was problem A? find the array. Okay, so we have an array A, and it's beautiful if for every I, AI equals 1, or at least one of these numbers exists. Okay, so if you start like playing around with different arrays, you realize that, I guess the easiest way to see this is consider the smallest element in the array. So smallest in array, let's say that's AI. So we know that either AI is 1 or AI minus 1 or AI minus 2 is in the array. But since AI is the smallest element in the array, these two cannot exist in the array. So AI must equal 1. So we know 1 is in the array. So now what are we trying to find? The minimum possible size of a beautiful array with sum of elements equal to S. So essentially, we want to try and maximize the sum with the minimum possible size. And we can easily construct some array that has sum less than or equal to the maximum possible sum. It shouldn't be too hard to see that. So if we have 1 in the array, from this condition, AI minus 1 or AI minus 2 must be in the array. And for the next smallest number to be as large as possible, we want AI minus 2 to be in the array. So then the next smallest one would be 3. Similarly, the next smallest one would be 5, then 7, then 9. So these are just the odd numbers. So the sum of the first n odd numbers is n squared. So we want the minimum possible size with sum of elements equal to S. So this would just be the smallest perfect square that's greater than or equal to S. Right? Because if we have size n, where n squared is the smallest possible square that's bigger than S, then we can construct an array with sum S, because we can construct an array with sum n squared. So yeah, the answer is just the smallest possible n, such that n squared is greater than S. Greater than or equal to, sorry. Then here's my implementation. I was worried about precision error when taking the square root, but I don't think it should be a problem. Okay, so problem B. Maximum cost deletion. Oh, this problem. So yeah, we delete consecutive substrings of equal characters. So when you delete a substring of length L, you get A times L plus B points. So let's say we have 0, 0, 1, 1, 1, 0, 1. So you get A times L plus B points. So the thing to notice is that if you sum these over all the operations you do to delete the string, this is the sum of A times L plus the sum of B. So this is A times the sum of L plus the sum of B. So the sum of L is actually constant because over all the deletions, L will sum to the size of the string. So this part just becomes A times N. And now the sum of b. So this is just b times the number of deletions. So this is our answer, and we want to try and maximize this. This first term, a times n, we can't do anything about because a is constant and n is constant. But for this second term, b is constant, and we can change the number of deletions. So if we want to maximize this and b is positive, if b is greater than 0, greater than or equal to 0, it doesn't really matter, then we want the number of deletions to be as large as possible. And since we delete consecutive substrings of equal characters, we can just delete every individual character one by one. So then that would just be a times n plus b times n. Right? Since b is positive, we just want to add it as many times as possible. But however, if b is negative, then we want the number of deletions to be as small as possible. So the smallest possible number of deletions. This is a slightly harder problem. So we have these contiguous runs, sort of. Here there are 4 of consecutive zeros and consecutive ones, consecutive zeros. And if there are 3 runs, the number of deletions only depends on how many runs there are. So if you notice how when you delete one run, then 2 runs merge together. These 2 merge together. So you can either sort of create a recurrence, like the answer for 4 is just the answer for 2 plus 1, and the answer for 3 is just the answer for 1 plus 1. And you can do that. Actually, that's not too hard. Let's just write it out. So an equals an minus 2 plus 1, where an is the minimum number of deletions if there are n runs. So here there are 4 runs. So we know this is true, since if we delete 1 run, that gives us 1 deletion here, then 2 runs merge together. So if we delete 1 run, there are n minus 1 runs, but 2 runs also merge together, so that gives us n minus 2. And then if we have the base cases, a1, that takes 1 deletion, a2 takes 1 deletion, then you can easily just deduce a simple formula. So it turns out to be a times n plus b times, I think it's the floor of n plus 2 over n. No, the floor of n plus 2 over 2. So that's problem B. Sorry if my handwriting is really bad. Problem C. Okay, Manhattan subarrays. This problem I thought was pretty nice. So we have the definition of Manhattan distance. If you don't know what that is, let's say you have point A comma B and C comma D. Manhattan distance is just the difference in the x's plus the difference in the y's. Yeah, it's defined here. So 3 points form a bad triple if the Manhattan distance of P and R equals the sum of the Manhattan distances of P and Q plus the Manhattan distances of Q and R. So let's say we have a point P and a point R here. Then you notice that if Q is anywhere in this rectangle, it forms a bad triple. Similarly, if R was here, if Q is anywhere in this rectangle, whoops, what happened? Then it's a bad triple. So the thing to notice is that if P, Q, and R, the X's are all increasing and the Y's are all increasing. Okay, let me reword this. For P, Q, and R, if either the X's are all increasing or the X's are all decreasing, and the Y's are all increasing or the Y's are all decreasing, then they form a bad triple. Because if you think about it, if Q is anywhere outside the circle, then we'll have to do some redundant moves or some unnecessary moves that don't make it optimal. So everything, if Q is within here, the distance from P to R, the minimum distance from Manhattan distance from P to R can go through Q. Sorry, that was probably a really bad explanation, but you can look at the editorial if you want a better explanation. So then we have an array is good if it's impossible to choose three distinct indices, I, J, and K, that form a bad triple. So if we consider these in this order, where I, J, and K are in order, if BI, BJ, and BK are either all increasing or all decreasing, then it's a bad triple. Because we already know I, J, and K are in order. If we just choose them, like choose three of them. So essentially we just want to find the number of good subarrays. So a good subarray is a subarray that, right, it's impossible to choose three distinct indices. So all we have to do is, since the Y's are already in order, since they're the indices, we just have to look at the array. So let's consider the first example, 2, 4, 1, 3. And we just have to see which of these subarrays have no three indices that are monotonic, that are either all increasing or all decreasing. So in this case, every subarray you can think of, there are no three indices that are all increasing and all decreasing. And it turns out that the maximum number of, like the largest possible size like a good subarray can be is bounded. So if you sort of like play around, you can realize this. But also, I mean, we can take the second one, for example. 69196. So for example, if you look at this subarray, 6, 9, and 9, they are monotonically increasing. So this is a bad array. But yeah, there's probably a easy, better proof for why the size of a good subarray is bounded, but yeah, you can look at the editorial for that, but I just proved it by AC. Okay. So yeah, once you have that it's bounded, you can just loop through, let's say it's less than or equal to 6. You just loop through all subarrays that have length less than or equal to 6, and then brute force it. So choose 3 random indices. So that would be like 6 choose 3 times how many subarrays of length less than or equal to 6? That's like 6n times n. Or sorry, 623 times 6n. Yeah. So that's like 120n. So that's should run in time. But that was probably a really bad explanation, so just look at the editorial. Okay, problem D. So we have n, l, and r, right? So the first thing to do is understand what this means. So an array is excellent if this big F of A is the maximum among all good arrays of size n. So how do we calculate this? Let's first analyze that. Move the board. Problem D. Okay, so AI plus AJ equals I plus J. So we can rearrange this to AI minus I equals J minus AJ. AI minus I equals negative of AJ minus J. So here this tells us something interesting, is that if we subtract I from every element, so subtract 1 from this, 2 from this, and from this, then we want the number of pairs. So F of A is the number of pairs in this new array. In this new array, if we sum these columns, the number of pairs such that one is the negative of the other. So how do we maximize that? Well, this is just maximize. It shouldn't be hard to see that it's maximized when half of them are like plus x. And then the other half are negative x. Because here it's like n over 2 times the floor of n over 2 times the ceiling of n over 2. And it shouldn't be hard to prove it with math, but yeah. So that tells us whether an array is good. So we need these sums to be a1 minus 1, a2 minus 2, an minus n to look like this array. So we also have this bound that AI has to be between L and R. So how do we deal with that? Okay, so the way you can count this is, let's say we have let's say you have R, and R, wait, let me think for a second. Okay, yeah, let's say you have some K that's one of these. This represents one of these. So K plus X, if K plus X is greater than R, then this value must be negative X, because all of these have to be within L and R. if k plus x is greater than r, then this has to be fixed to negative x. So this gives us the condition that x is greater than, k greater than r minus x. Every k that's greater than r minus x is fixed. We know what value there are. And similarly, if we have some k over here, if k minus x is less than r, this is equivalent to k is less than l plus x. We know all of these must have positive x, because if they had negative x, then this condition would break the fact that AIs are between L and R. So k is less than L plus x, all these are fixed. K is greater than R minus x, all these are fixed. And the rest of them, we can order however we want. So the way we count this is we find where L plus x is. Say L plus x is here. You find where R minus x is. R minus x is here. Everything below this is fixed. Everything above this is fixed, and the rest we choose. So in this case is 3 choose 1 here. So this, we can just check all x's. Loop from x equals 1 to x equals, there's some upper bound we have, so we can just it's not too hard to calculate that x must be less than or equal to r minus l plus 1 over 2. I left that calculation out just because it's boring. And then you're thinking, if we loop from here to here, since L is between, L can be really big and L can be really small and R can be really big, this can be really big. So if we loop through everything, it'll take too much time. But so I guess the thing to notice is that as x gets bigger, once one of the x's, so let's say L plus x hits 1 first. So once we know L plus x hits 1, then we wait sort of n over 2, we can brute force calculate n over 2 turns, and then once L plus x is here, or let's say once L plus x becomes here, all these must be positive x, but that's a contradiction since we don't have that many positive x's. So we can loop from the first time L plus x equals 1 or r minus x equals n. So here loop from x is 1 minus L, the minimum of 1 minus L to r minus n. Loop from here a linear number of times. So loop from here n times, and then the rest of them will be impossible because L plus R is too far ahead, or R plus X is too far behind. So there will be too many negative X's here, and we don't have that many for the array to be good. Remember, we only have a fixed number of negative X's and positive X's, because if there are more positive X's here, then it's not good. F of A is not maximum. Remember, we have n over 2 x's, the floor of n over 2 positive x's, and the ceiling of n over 2 negative x's, and vice versa. So all we have to do is loop from x equals this to x equals this to x plus like n over 2, or you can just loop to x plus n just to be safe, and sum all those binomial combinations we said earlier. So like a certain number of the starting ones are fixed, a certain number of the ending ones are fixed, and then the rest of them you can, It's just a combination. So you choose where the positive x's are. So this one you can calculate using that. And then for the ones before, x equals 1 to minimum of 1 minus L or minus n, there are no restrictions here. So here it would just be n choose n over 2 for each one of these. So if we sum all that, then we'll get our answer. There's one thing to be careful about, is that if n is odd, then we can have either the floor of n over 2 positive x's or the ceiling of n over 2 positive x's. So you have to be careful about like multiplying by 2. But yeah, that's the general sketch, and you can look at my code for details. So here we start out by just adding this part, n choose n over 2 times the number of turns at the beginning, and then here we loop from that to that plus n. So if n mod 2 is 0, then there are n over 2 x's plus x's, n over 2 minus x's. So then we subtract the number that are fixed, and then we add this binomial combination. And similarly here, but there are two cases. So this is the first case, this is the second case. Here, this is how many negatives there are, this is how many positives there are, and we subtract the number fixed, we add the combination, and do the same thing here. And then we get our answer. So yeah, that's problem D. Thank you for watching, and I hope you had a good contest.